Today I'll talk about tensor network quantum circuit simulations, and in particular I'd like to bring attention to importance of how you actually formulate the problem of simulating a quantum circuit using tensor network. So first of all, what is a quantum circuit simulator? It's just a classical code that emulates the runtime of a quantum device on a classical device. And we might use these simulators as a debugging tool of quantum algorithms, or we might use for optimization of parameters for variational algorithms. We might also verify quantum advantage claims. So in general, it's just a nice piece of code that runs your quantum circuit. And this is a general overview of the simulation workflow. First, we take a problem. For example, I will focus on QoA and max cut application of QoA. So the problem would be a graph. And we take a problem, then we formulate a quantum circuit from this problem. Then, depending on what quantity we want to simulate, we create a tensor network. And then our goal is to contract this tensor network in the most efficient way possible. So first of all, what is the max cut problem? It's a graph coloring problem where you have two colors and you want to color vertices such that you have maximum number of edges of different colors. And QoA is a variational algorithm that uses parameterized ansatz state to generate a state in which the measurement will give you a good solution to the problem. And in case of max cut, that would be a binary string that assigns the colors to your graph. And of course, and that circuit is parameterized by the structure of a graph and parameterized by the parameters, the QoA parameters. So first of all, you can see that the common way to translate the QoA cost gate is these three gates, C0, the Z to the power of gamma, and again C0. Well, in fact, we know that this gate, this 2-qubit gate, can be reformulated as a diagonal ZZ gate. And these three gates can be reformulated at the level of a gate into a single gate. Now, if we change this structure to use ZZ gates, you see that it is much simpler structure. So this is a first step of optimization at the step of formulating a quantum circuit. So now let's say we have a quantum circuit and we want to simulate something about quantum circuit. So in general, there are two interesting numbers that you want to obtain from a quantum circuit is the probability amplitude, or a batch of probability amplitudes, and a value of some expectation value of some observable. And depending on that, it will depend on how you construct the tensor network. But first, what is a tensor network? Well, tensor is a generalization of a matrix. And if, for example, a vector is a rank 1 tensor, it has only one dimension. Matrix is rank 2 tensor, and a cube of numbers. So an object that has 3 dimensions would be rank 3 tensor. And these objects are a very natural representation of how quantum operations work on a quantum state. So there is a diagrammatic notation of a tensor of tensors, and in general, this means that if you have a tensor with n indices, it will be represented as a vertex with n edges. So you see, for example, here the C tensor is represented by a vertex with 3 edges that don't connect with anyone, but this is just a kind of a representation. If those tensors participate in the tensor network contraction, then those indices that are common, for example, here on the left is the example for just simple matrix multiplication problem everyone knows of. So here we have a common index J, and in this diagrammatic notation, we see two tensors that share a same index. So this is a tensor network for just matrix multiplication. For more complicated structures of tensors, this tensor network notation makes more sense, since you see the structure of your tensor network, and it really helps to visualize those tensor networks, and it helps to find the good order in which you evaluate this tensor network. So the evaluation of tensor network is basically just contracting all the indices that are inside, that are shared by tensors. So we see the I, J, and K, they are not shared by any two tensors, so they are our fixed indices. But those that are inside, we imply that there is a summation over those indices. And we want to calculate this sum to evaluate the values of tensor D. When we contract two tensors, basically of the same size as here on the left, the memory required to store the result grows, because here, if we have two tensors of shape 4 dimension, each of shape 2, each of length 2, and we contract this common edge, the resulting tensor will have a lot of indices, and it will require much more memory to store. In general, it scales exponentially as the tensor rank increases. And it's really important to find the good order in which you contract, so your tensor size doesn't grow. This is effectively a bottleneck. The largest tensor that you obtain through your contraction determines whether you are able to simulate the quantum circuit or not. So how do you convert a quantum circuit to a tensor network? It's quite easy. Each gate is already a matrix. So we map directly each qubit to an index and gates to tensors. These are just 2 qubit gates for single qubit gates, but for 2 qubit gates, you will need 4 indices, 2 input indices and 2 output indices. And the structure of the tensor network looks exactly the same as the structure of quantum circuits. So I effectively can say that this here is also a tensor network if we say that these rectangles are vertices. And in tensor network representation, instead of using state vector, we use also a tensor that represents your state. But in fact, it's a very important point that in course of your contraction, when you contract, you don't actually store a state. There is no such notion as a state of the system at time t, because you don't contract those edges in order. You contract them arbitrary, well, not arbitrary, but you contracted them in that order so that it minimizes the size of the largest tensor in the contraction. Okay, so now that we constructed a tensor network, we want to find a good contraction order. We use what's called a bucket elimination approach, in which you select index and then get all the tensors that have this index, and then contract this index, and the resulting tensor will have the union of all indices of those tensors that have this selected index. And to get the order in which to contract those indices, we use a line graph of a tensor network. A line graph is a transformation of a graph where each index is converted to a fully connected subgraph, and each edge is converted to an index. So for example, here, if we have 1 qubit gate, this is also can be considered a tensor network, and it will be converted to each edge will be converted to an index, and the node will be connected to a fully connected subgraph, which is just an edge. And this is an example for 2 qubit gates, and these are non-diagonal. But okay, so this is just the previous contraction that I showed earlier, but in terms of line graph, you see that A and B are fully connected subgraphs on 4 indices. When you contract, you have a fully connected subgraph on 6 indices. And what we want to is we want to find the contraction order such that the number of neighbors of vertex that we eliminate stays as low as possible. But what if we look at the structure of each gate, of each tensor that corresponds to a gate, and we see that all values that are not diagonal, they are 0. And we can simplify the representation of this tensor by basically equating the indices here on the right hand, indices I1 and J1, they will be the value of tensor will be non-zero only if those indices I1 and J1 are equal. So this is effectively, there is a Kronecker delta inside. And we can represent this by much simpler structure in our line graph. So this is just a mathematical formulation of how you describe a tensor that has only diagonal values, non-zeros. And if you, for example, on the left-hand side, this is a line graph for just the simplest way of constructing a tensor network with original gate definitions and without diagonal simplifications. If you apply the diagonal simplification, you see the line graph is simplified, and if you apply the ZZ gates that I mentioned earlier on the level of circuit, you see that the line graph is much simpler, and it translates into computational efficiency as well. So this is the number of floating point operations to simulate QoA's ansatz state amplitude, and it is plotted within number of qubits. And so floating point operations, it's just arbitrary metrics of how fast can you simulate. In general, you can count on simulating gigaflops. For example, these number of qubits, 150, should simulate in the matter of seconds. This is very powerful approach, especially for shallow circuits that have p+1, and you are able to simulate amplitudes for vast number of qubits, 150, which is impossible if you use state vector evolution, for example. And you can see that the diagonal gate simplification, so here it will be this pink line compared to just vanilla or even without ZZ gates, but without diagonal. It reduces really by the orders of magnitude the complexity of your simulations by up to 2 orders. Well, it's actually 4 orders of magnitude. So the simplifications that you get in terms of line graph translate very hard into efficiency in your simulation, since reducing the number of neighbors, reducing the index count of a tensor even by 1, you basically halve the memory required and also the computational resources that are required.
Daniela, we need to wrap up your presentation.
Oh?
I said you need to wrap up your presentation.
Okay, good. Yeah, I think I'm mostly done. This is the same plot, but for energy evaluations. And these are some numbers to calculate expectation values for 1,000 node graphs for different p's. So the best results that we have is 1 minute to calculate p equals 5 and degree 3 random regular graphs. And this is it. Thank you for your attention.
Oh, wonderful. Thank you for the presentation.